Now we start with a new model, the interference channel. So in this case, we consider two sources who gives their output to an encoder. So encoder 1 and encoder 2 both produce a sequence of length n, x1 to the n and x2 to the n, which goes through a channel. And the channel puts out y1 to the n and y2 to the n, depending on the two inputs x1 to the n and x2 to the n. These sequences go to decoder 1 and decoder 2, and they have to make estimates of W1. So decoder 1 want to estimate the message of encoder 1, and decoder 2 want to estimate the message of encoder 2. So, and our goal is again to find the set of rate pairs R1, R2, for which we can make the error probability that the estimate of the first message and the second message is not equal the first message, and the second message is an arbitrary small number. That means, like every time if n goes to infinity, so the block lengths go to the infinity, the error goes to 0. So the interference model involves several types of communication scenarios with many users. For example, we can again look at the cellular radio system. One often has their interference from neighboring cells, or perhaps even with a cell if one is using code division multiple access. And if there are two mobile stations, then the model describes the essence of the coding problem. And interestingly, the capacity of the interference channel is still not known in general. The first simple property is one similar property we also have for the broadcast channel. And this property is that the capacity only depends on the marginals, so somehow on the marginal channels. So if you look at the capacity region, then it really depends on the marginal channels from x1, x2 to y1 and from x1, x2 to y2. That means the capacity region is the same for Z channel here with y tilde and y1 tilde and y2 tilde, and y1 and y2 if the marginal channels are the same. And the proof is exactly the same, like, or is similar to the broadcast channel. You look at the two probabilities, you look at the sum of the probabilities and the individual maximum of the probabilities, and then you can show if one goes to 0, then the other goes also to 0, and if for one channel the probability do not go to 0, then the other cannot go to 0 also. That's the idea of the proof. And I think you just should go back to the slide where we do it for the broadcast channel. Look at this, and you really will immediately understand how the proof works.